Hey guys, so we're going to start chapter 9, which is, this chapter is about chemical formulas. So it's very related to the reactions 1 and reactions 2 labs that we sort of are working on right now. We did 1 already, but we're finishing reactions 2. So the thing about it is, in order to do chemical formula relationships, in order to be successful in this chapter, we need to understand chemical nomenclature and how to make something go from a name into a formula. Okay? Or the other way, formula into name. Both ways are important. So the prior chapters are critical for success in this chapter. Okay, so in this slide, what we're seeing here is a return to a lab we did before, the percent composition lab, where we took potassium chlorate. And I do expect you to know that name because it's, for one thing, something we used in lab, but also the chlorate group is on the back of your periodic table. So really all you've got to remember is to look there because we have more than 2 atoms. So that means it's got to be a polyatomic group. And then over here we have just 2 atoms, so it's not polyatomic, it's just potassium and chloride. Okay, so we took potassium chlorate, we heated it up. You can show heat by putting a little triangle over it, over the arrow here, and it produces potassium chloride and oxygen gas. Okay, so if we want to do a percent composition, that's basically part over the whole times 100%. Okay, so percent composition is just the part of interest divided by the whole. All right, well, the whole in this one is our starting material, the KClO3. All right, so for example, if we want to know the percent composition of oxygen here, okay, so oxygen is one of our products. If I know how much material I started with, 1.42 grams in the beginning, and I know how much solid I end up with, that's the potassium chloride, that's 0.93 grams, I can figure out how much oxygen is made just by subtracting, because this weight is going to add up to KCl plus whatever oxygen is. So basically what we're going to do here is rearrange this to solve for the question mark. So we have 0.49 grams of oxygen that was made. Whoops, grams. O2. So this is from experimental data, so it's something I gathered in the lab. So I can find out the percent composition by taking the amount of oxygen and divided by our starting material. So that's the part due to oxygen divided by the whole, which is what I started with. And so I'm just plugging it into the percent composition formula. And the calculator tells me it's 0.345 before I multiply by 100%. Well, I only have 2 decimals because of my subtraction here. When we subtracted, this has 3 significant figures, but when you subtract its place value, so we can only keep the hundredths place, so hundredths place here. Which means I only have 2 significant digits in my answer. So 34.5070 blah blah blah. That's going to round to 35% because I only have 2 numbers I can keep. So I'm going to record that. So that's experimental. You're going to have grams divided by grams. Your oxygen divided by KClO3. The theoretical percent, this comes from the periodic table. So we did this together in class, or in lab rather. But here it is again, just to remind you. I have to pull the masses of these things from the periodic table. So let's take a look at my periodic table here. So oxygen has a weight of about 16.00. Okay, so if I'm trying to figure out the weight of O2, it's going to be 16.00. And the unit on the periodic table is actually something we're going to learn about very soon called grams per mole. or you can think of it as 16.00 AMUs. Either way is fine. There's 2 oxygen atoms, so 16 AMU is what one of them weighs. They don't weigh anything. They're atoms. I don't know why I was going to say that. That's silly. So in order to figure out the weight of oxygen gas, O2, we have to multiply 16 times 2. And again, AMU and grams per mole are essentially the same thing. So now we know the weight of the oxygen, so that's going to go on the top of our fraction. On the bottom, we're going to put the weight of KClO3. Okay, so we already know that the oxygens are 16, so I'm just going to fill that in. The potassium and chlorine are on the periodic table, so chlorine here is 35.45, let's call it. And potassium is 39.0983. Let's say 39.10. And the reason I'm choosing to round to 2 decimals, it's kind of an arbitrary choice, really. This is actually 16.00. The reason I choose that is because typically 4 significant figures is more than enough. In this case, we only have 2 anyway, so I really don't have to go 4. I could go 3. But I just do it because 4 is usually enough, and it's kind of a habit. All right, so if we add up 3 times 16 plus 35.45 plus 39.1, we're going to get a total of 122.55 grams per mole. So that's the weight of the KClO3. Now, to figure out our theoretical percent composition, what I have to do is take the oxygen divided by the KClO3. So it's similar. We got oxygen on top here, we got KClO3 on the bottom here. We're going to do kind of a similar thing, but this time the numbers came from the periodic table. Okay, so this whole fraction is going to get multiplied by 100% to turn it into a decimal. So we go 32 divided by 122.55. And it says 0.2611179 and a bunch of other stuff. We only have 2 significant figures in our other data, so I'm just going to keep 2 here. That would be 26%. Okay. Now, for our percent error, or percent difference, this is actually more of a percent error. The 2 terms are, it's basically the same equation. They just have a little bit different meaning. Percent error means how far from the right answer am I? Okay, and so looking at 26% and 35%, those are pretty different. But let's see exactly how far apart they are. These little lines here mean absolute value, so I need to pay attention to that. I cannot ever have a percentage that is negative. You can't get negative 10% on a test, right? Hopefully. So here we're going to take the experimental value. That's the one that came from the lab. It's in grams. So that's 35% for our example here. And I'm going to subtract the theoretical value. That's always the one that comes from the periodic table. So 26%. Theoretical means in a perfect world, this is the result we would expect. Okay, and so the masses on the periodic table are, you know, the true values. And so we're using this as a way of telling how close to the actual value we are. 26 goes on the bottom. These are all percents, by the way. And then I'm going to multiply that whole fraction by a percentage as well. So we're going to take 35 minus 26 on the top, and you get 9. Then you divide by 26. That says 0.34615 and a bunch of other numbers. I don't need all of those because I only have 2 significant digits. So as it turns out, my error is going to be 35%. That means I'm about 35% wrong. That's not horrible. It's not great either. I would say that's probably average for this experiment. In an ideal world, we would have measured different masses in here. They would have been, you know, less oxygen generated, so this number is smaller. So something about my experiment meant that I had too much oxygen. Probably I didn't wait until the KClO3 was fully dry to do my next weights. All right, so the next topic here is kind of a review of what we already know. So CO2's Lewis dot structure, if you recall from prior chapters, looks something like this, right? So the little 2 here means that we have 2 oxygens which are each attached to the carbon. That means that total I have 3 atoms, and I can obtain that without having to draw the Lewis structure just by counting the subscripts, right? So if there's a subscript, like 2 here, means I have 2 atoms. If there isn't one, it implies it's sort of a hidden number 1. We don't usually write the number 1 because if you don't have a number there, we assume it's 1. So in this case, all I have to do to figure out my total number of atoms is to add 1 plus 2. So we got 3 total atoms. Propane, C3H8, similar idea. We can just take the 3 carbons and the 8 hydrogens and we add them together. So we get a total of 11 atoms. This one's a little different. We have parentheses here, and so this subscript applies only to what's inside the parentheses. In this case, the oxygen and the nitrogen. You can visualize this by kind of drawing a little picture. When we have parentheses, this whole entire group is what's attached to the nitrate, or to the calcium. We have a nitrate attached to calcium and another nitrate attached to calcium. That's because calcium is +2 and nitrate is -1. So we have to have 2 of them to balance the charges. Now, in order to count up our total atoms, this 2 in the subscript has to be distributed to everything inside of it. So what we get is, for oxygen, we have a subscript of 3 on the inside of the parentheses times the subscript outside of it. So we get 6 oxygen atoms. Nitrogen is a 1 on the inside times the 2 on the outside. So we have 2 of those. And calcium isn't part of the parentheses, so this 2 does not apply to calcium. It's outside of that. So we would have 6 plus 2 plus 1. So we get 9 atoms. I want you to tell me how many atoms does KClO3 have, and I'll grade it when you turn in your notes. So go ahead and pause it for a second and do that right now. You guys are having a hard time remembering to go back and do it, so make sure you do it. Okay, so one of the tasks we have in lab is to translate from words into formulas and equations. Okay, so we did this in Reactions 1 lab, so I'm going to show you an example of one of the harder ones to interpret. Okay, so reaction 3 is a little complicated because actually 2 different reactions are occurring. And when we wrote this one up, a lot of people had a difficulty with it because you would be in the habit of sort of reading the beginning stuff, the reactants, so tin 2 chloride and hydrochloric acid, and that's how you'd start to write your reaction. And then it says you add 2 to 3 pieces of zinc, so a lot of people were writing like 3 different reactants kind of all together. We don't have any types of reactions that might use 3 different reactions, except for maybe a combination reaction. But that's not going to work here because we have 2 metals in one spot and they're not going to combine together. So the trick here is more of a reading exercise. What we have to do is get to this part where it says you will observe 2 reactions occurring, right? And so that is trying to narrow down our vision. It kind of matches how the report part of this lab was laid out. It says that there's 2 reactions. So it's kind of a connection between what you're writing in your report and what the procedure says. And so that clues me in that I want to pay attention to whatever comes after that. And it says the tin 2 chloride will react. Okay, so tin 2 chloride, we're going to put that down. Tin 2 chloride. And then it says will react with. So will react with is a plus sign. The zinc, so zinc is Zn. If you don't remember that, of course, you go look in the back of your book and it has an alphabetical listing. And then it says producing. So producing means arrow. Sometimes it says yields too. Yields a solution. It could do that. A solution of zinc chloride. So zinc chloride. So Zn. Oh wait, mixing up my steps here. Whoops, I messed up. I'm trying to go too far ahead. Now, if you feel like, if you do this, it's going to make it harder to interpret things. So don't do what I just did. Instead, what we're going to do is we're going to just take the words out of the paragraph and write them down. And then we'll worry about translating it in a second. Okay, so it said zinc chloride solution, to be specific. It said a solution of zinc chloride. And it also says the tin 2 chloride is a solution earlier on, right up here. So I'm going to put solution there also. Those are important clues to help us write the reactions. Okay, and so the zinc, producing a solution of zinc chloride and elemental tin. So tin. That was an invisible T. There we go. Tin. So this is plus tin. So we have the bare outline for this reaction just by writing the words down. What we're doing is zooming in on the important things in the paragraph. So you're ignoring a lot of words that you don't need. This is a very big paragraph to try and follow along with. So instead, we're going to just take the words and write them down with the right symbols and format to be ready to put it into a chemical formula. The other reaction is also in here. It says also the zinc will be consumed, so zinc. Only about half my letters are showing up. This is kind of weird. The zinc will be consumed by the hydrochloric acid. So if it's being consumed by it, that means that they're reacting together. Okay, so I'm going to put hydrochloric acid there. To produce, that's arrow, hydrogen gas. Okay, so we're going to write that down. I already know the state for that one because it already gives it to me. And a solution of zinc chloride. So zinc chloride is another product. That's the same product we had in the other reaction, so that's pretty interesting. There is a connection between those two things. Okay. So now once we have the words written down, I like to do this on a separate piece of paper because there's not a lot of room usually on the test or the, lab report. So I go through a lot of paper when I write reactions. So we're going to start with the red one, tin 2 chloride, it says. So the symbol for tin is SN. That's another one we might have to look up in the back of the book. The 2 plus does not mean that there's 2 tins. That means it's the charge that the tin has. Okay, so it's really, really important. I saw a lot of people messing this up. To understand that the Roman numerals mean charge, not how many tins. So we're not going to write SN2 like that. That's wrong. That is not what's going on here. We need to know the charge of it so we can figure out how many chlorine are going to go with it. So if it's plus 2 and the chlorine is a minus 1, that means I have 2 electrons to give away and chlorine can only take 1 of them. So I have to have 2 separate chlorine to do that. So SnCl2 is tin 2 chloride. Now you'll notice that there's no Roman numerals in here and no charge. Write that down. In the chemical equation, there's no Roman numerals and no charges in compounds. In other words, another way to think of that is if I add up all the charges, they should add up to 0. So -1, there's 2 of those, so that's -1 times 2. So plus 2 plus -2 equals 0. So that adds up to 0. That's what our compound is. Okay, so this is a key idea when you're writing formulas. 2 ideas, really. All right, so we got tin 2 chloride, and it says solution. It said solution. Solution means AQ, always 100% of the time, no exceptions. So that's easy. And then it says zinc. Zn is zinc. This is probably a solid because it's a metal. You would know because you did this reaction. So as you go along, you're supposed to try to assign these when we were doing these reactions, because that way you'll have the zinc in your hand and you know whether it's a solid, a liquid, or a gas. It's an element, so it can't be aqueous. Elements don't dissolve in water. They only react with water, if sometimes. So we couldn't write zinc AQ. That wouldn't make sense. All right, and then so it says zinc chloride is produced. So we're going to take that Zn and pair it up with the chlorine. We look at the periodic table and it turns out zinc can only be a +2 and chlorine is a -1. That means, again, I have to have 2 chlorine to make this a balanced compound. And then it says solution again. Okay, so that means AQ. And then finally our other product is tin, which is just SN. It's a metal, so it's solid. And I know it's metal because it's to the left of the stairs on the periodic table. All right, so we're almost finished with balancing this reaction. I'm going to clear some space here so we have a little more writing room. All right, there. So one thing we got to check is to make sure that the reaction is what we call balanced. So what we did here was charge balancing, +2 and a -2 for total charge. When we're balancing the whole reaction, we're trying to make sure that we have the same number of each type of atom in the beginning that we have at the end. And we'll go over more details of this in a bit, but these are the components of our reaction. So I have 1 tin on this side and I have 1 on this side. I have 1 zinc and 1 zinc, and then the chlorine I have 2 here because there's a subscript, and over here I have 2. So this reaction is balanced as written. It looks great. It's perfect. Okay, so we're gonna leave it as it is. I don't need to change anything. Okay, the other reaction, the blue one here, starts off with zinc, so Zn. And we decided that was a solid because it's an element. And hydrochloric acid. Hydro in our naming scheme means there's no oxygen. So I would not pick any of the stuff off the back of the periodic table because they all have oxygen. And then I know that acid means H in the front and AQ at the end. So I just got to figure out what the chloric means. Chloric is chlorine. So hydrochloric acid is HCl AQ. Cool. All right, then the next thing it says is it's going to make hydrogen gas. Hydrogen gas. A lot of you were writing this. And hydrogen does not exist in nature anywhere, actually, even artificially, as just H. The only thing that we can have, if it's the element, which this is it has to be diatomic. You need to remember all the diatomic elements. Elephants are made out of way more than 2 atoms. We have to remember all the diatomics because they come up like this. When it says hydrogen gas, that means H2, not H. So our mnemonic for that was have no fear. Oh. So F is fluorine. Have no fear of, O is oxygen, ice, cold is chlorine, not carbon. People mess that up a lot. And beer is bromine. So have no fear of ice, cold, beer. That's how we remember that from way back. All right, so H2 is the diatomic, and so I'm going to put H2, not H, for hydrogen gas. And then it says we also made zinc chloride, which is the same thing that we just worked out above there. Okay, now we got to check this one to make sure it's balanced. So let's see, we got 1 zinc on this side, 1 on that side. We got 1 chlorine here. Oh, I have 2 chlorine on the right. So in order to balance this, I can't change subscripts because +1 and -1 are already balanced. I can't add any subscripts, like I could not do this. That's against the rules because then we have a -2 with a +1 and that does not work. So instead what I have to do is put a number in front of the whole entire molecule. So I have 2 HCl's. That means now I have 2 chlorine because the 2 applies to the hydrogen as well as the chlorine. Okay, 2 chlorine and 2 chlorine matches, and then I'm going to balance the H. Oh, whoops. Apparently I can't click there. There's 2H now because we put a 2 in the front of it, and there's 2H over here as well. So just putting a 2 in front fixes the chlorine and the hydrogen, which is great. So our 2 reactions, to answer this question from last the last experiment we did, are right there. All right, so this is the pattern we want to use whenever we're asked to write a reaction. First, we take the words, the important parts of this giant paragraph, some of which is good for writing the reaction, and some of it was about how do you do the experiment. Okay, so we take these words and we pull out the important pieces, and we set them up in the format of a chemical reaction, and then all I have to do is interpret from there into chemical symbols. Okay, and as we're interpreting, we have to balance the charge. That's +2, -2. That whole business has to be done each time for every compound. Otherwise, I'm going to end up making something that is impossible. Okay, so some definitions here. The arrow we have called yield or produces. Okay, those are the vocab words we use with it. S in parentheses after a chemical means a solid. L means liquid. G means gas. And AQ means dissolved in water. Okay. Finally, the triangle means heat. So I showed you an example earlier, the KCl decomposition, where you put the heat over the arrow, and that shows that the reaction doesn't automatically go all by itself. You got to put in a little bit of energy first. All right, I want you to fill in these definitions. Use your words, not Google or your textbook or Wikipedia. Okay, I want you to tell me what you think a reactant is, a product, a subscript, and a coefficient. And especially, what is the difference between these two things and these two things? Okay. So here's what we did. Here's our strategy for making balanced equations. Our purpose is to basically obey the law of conservation of mass, which says that you cannot create or destroy atoms. You have to start with the same number of carbons that you have at the end. You can't make them from nothing. All right. So in order to do this, first we write the words down. Then we write the unbalanced reaction. This is where we are messing with the charge, okay? The charge, that's the important thing here. So step 1 is writing down the words. Step 2 is translating those words and figuring out what charge the compounds are, the pieces of the compound are going to have. So we're balancing the charge. That is where we use subscripts. Oops, I don't want to highlight it. I want to write. So step 2 is where we get to mess with the subscripts. After that, they're stuck. You cannot change them. They are what they are. No take-backsies. Okay. In step 3, we're going to balance atoms on both sides. And this is where we get to mess with... I did it again. That's annoying. Where we get to mess with the coefficients of the balanced reaction. So step 2, we're doing charge, which is subscripts. In step 3, we're doing coefficients, which is balancing mass. Don't mix the two steps up. You can't do them both at the same time, because then you end up creating compounds that don't exist. You end up creating something impossible. Okay, so we want to make sure to only create chemicals that actually exist in our balanced reactions. When we balance, it's important to follow the right order because it'll minimize the back and forth. Otherwise, if I start with, if I started with oxygen, you're going to end up going back and forth and changing things a lot of times. If I start with metals and then do nonmetals besides oxygen and hydrogen, and then focus on oxygen and hydrogen, it turns out that you don't have to go back and forth as often, so it's a more efficient approach. I highly recommend that you do that. Because sometimes when we write a coefficient in front of something, it's going to unbalance something else. So at the end, we also want to double check. Step 4 is always double check. All right, so for example, we're going to take these words and we're going to turn this into a formula. I just moved mine onto another slide, so it's a little bit easier for me to fit it in. But so first, step 1, we're going to take the important words from the reaction. In fact, some of you are really good at this. You're really good at highlighting important things. So for example, silver nitrate, that's a key thing because it's a chemical name. And it reacts with hydrogen sulfide, so there's another chemical name. At this stage, I'm not worrying about what that means. I'm just looking for important bits. Silver sulfide is the next important part. And then nitric acid. So there's our chemicals. Okay, those are the names of all the chemicals involved. And so then we're going to take that and just kind of write it in the format that we use. Reacts with this phrase here, this always means plus. So does and, they both mean plus. So silver nitrate reacts with hydrogen sulfide. So I'm just pulling out the important words so that none of the other stuff gets in my way. This is a reading technique more than it is chemistry. And it produces silver sulfide. So silver sulfide's going to go here. That sounds kind of like a superhero, like the silver surfer. Oh my gosh. Only sulfur smells really bad. So maybe that's not a superhero. Maybe they're a villain. And then it says nitric acid. So we're going to write that down. Okay, so that's the first step. We just take the words and we write them down. In the second step, we're going to interpret these words and balance the charge. All right, so silver, if we don't know what silver is, we look in the back of the book and it says Ag. People confuse silver and gold a lot. Gold is Au because it's aureus in Latin, and silver is argentum. There's a little thing somebody made up in one of my classes once. Or maybe they got it from somewhere else, I don't know. But they said, aw, shucks, you got me gold. Get it? So Au is gold, Ag is the other one, silver. And then nitrate is not an element. If it ends in IDE, that usually means it's an element. Nitrate is something on the back of our periodic table. So we have to flip it over and check that out. You want to get into the habit of when you see a word like that, you recognize that it's going to be there. You flip it over and you find the formula. Also on the back it tells you the charge of nitrate is -1. The front tells you, of the periodic table, tells you that silver is a +1. When silver is a metal, so that's just, the shiny silver that you think about whenever I say the word silver, it has no charge. This is a review. We have an equal number of protons and electrons, so when you subtract them they add up to 0. When silver is in a compound, it has to give up electrons in order to connect with something else. So it means it has one extra electron taken away. So in the case of silver is element number 47. It's right here. Okay. So element number 47 has 47 protons. If it's connected to something, it gave up one of its electrons, so it only has 46. Oh wait, yes, that's correct. Okay, good. So we end up with a +1 charge. So this is review from another chapter. But the periodic table also tells you the same thing. It says that silver is +1. That's referring to silver when it's in a compound. So we have +1 and -1, so that's already balanced. I only need one of each of those, so we're done with that. And then the next thing we got is hydrogen. Okay, well, I know what hydrogen is. And sulfide. Sulfide is the element, just sulfur. If it said sulfate, ATE, the AT endings are all on the back of the periodic table. Okay, and so we check our charges. Hydrogen is +1, and the first choice that sulfur can have is -2. That's because it has the 6 valence electrons. So if I have sulfur, it's going to look something like this as a Lewis dot structure. Hydrogen only has 1 electron all by itself, so you would end up with this. Sulfur is not happy. It only has 7 electrons. 2, 4, 6, 7. That means we need to find someone else to pair up with, so it's going to find another hydrogen. That means I have to multiply our hydrogens by 2 in order to balance the charge. So +2 and -2 will cancel each other out. So that means I have to have 2 hydrogen. Now, I don't expect you to know this, but this is a gas, and we generated it by burning hydrogen over the water. We did that in one of our experiments before, so that's a gas. I wouldn't mark you off if you said it was a solid or a liquid. It's not AQ, though, because if this were AQ, it would have a different name. Hydrosulfic acid is probably what we would call that, because it's an acid, and that's what AQ means. But here this is not AQ, so it has a different hydrogen sulfide instead. All right, so we keep going. Silver sulfide. So Ag is still silver. It's still a +1. The sulfur is now connected to the silver. So we've traded partners. Ag goes to S, and probably the H is going to go to the NO3. So this is a double displacement reaction. I start with 2 compounds and I end with 2 different compounds. So silver's +1. Sulfide isn't changed. Double displacement reactions, the charges in the beginning are the same as the end. So I have a -2 for the sulfur and a +1 for the silver. This means I have to have 2 silver in order to make this compound work. And then it says nitric acid. Well, acid means H in front, AQ at the end, and I just got to figure out what to fill in. Nitric, ic is the key here. So ic acid only happens if you had an ending of ATE. Remember, I ate it and it was icky. So ATE, so nitrate is the thing, and nitrate is this NO3 group. That's -1 and hydrogen is +1, so we need one of each of those things. Okay, I'm going to clear some of our charges here just to make it a little easier for the next part. So I have enough room. So we've balanced the charges. That means I am done messing with the subscripts. I cannot change them anymore. Don't be tempted. It's always wrong. Okay. So in step 3, now we're balancing the entire reaction. So what I want to do is start with the metal and count. On the left side, on the reactant side, I have 1 silver, and on the product side I have 2. Well, that's not balanced. Right away, I'm wrong. Something has got to be fixed. I can't change the subscript, so I cannot make this 1 silver. So the only thing I can do is put a 2 in front of this entire molecule. So I get 2 Ags and 2 nitrates. So now I have 2. Okay. And the next thing I'm going to balance is going to be the sulfur. So again, it goes, in order: metal, non-metals besides oxygen, and hydrogen, and then we'll worry about hydrogen last. So sulfur is next. We have 1 sulfur on this side here, and we have 1 sulfur here, so that one's cool. I'm going to balance the nitrate as a group, okay, because it doesn't change. It's a nitrate in the beginning and a nitrate in the end. I don't need to balance the nitrogens and oxygens separate from each other. This is always true for polyatomic groups, so look out for them. When you have a polyatomic group, they're easier to balance if you keep it together. So this too applies to the silver, and it applies to the nitrate. So now I have 2 nitrate on that side. I only have 1 over here. I just got this 1, so I have to put a 2 in the front of this to make it so I have 2 nitrate. And the last thing we're going to balance is the hydrogen. I have 2 hydrogen on the left because I have a subscript, and I have 2 hydrogen on the right because I have a coefficient. So everything balances. There's 2 silver, 1 sulfur, 2 nitrates, and 2 hydrogens. So this is our complete balanced reaction. The only thing that it's missing is the states of matter. Now, we learned in the most recent experiment about using this chart. And I did find an error on this chart. I just wanted to tell you about it. I wouldn't mark you off for it. The one I give you in the lecture notes is a little different anyway. But this here with ammonia, all the ammonium should say soluble. So S's all in this column. All right. You can fix that on your copy if you like. I just wanted to be diligent and tell you that I had discovered that this was wrong. Okay. So what we have to do here, the last step, the last thing I want to do is figure out whether these substances dissolve in water or not. This is definitely ionic. We talked about how ionic things are not going to be liquid. And you could observe this in lab when you did this experiment. If you did this experiment, you would be able to see whether it looked like a liquid. And if it does, that means we'd write AQ. If we're not doing this in the lab, then we need a resource to help us out. So I'm going to see what happens when I look at the chart for silver and nitrate. Okay, so the negative charges are here. So nitrate is this line, and the silver is a little bit higher up. So it's just easier to see if you have a printed version of it. Okay, I had to zoom out pretty far in order for you to see this, but on your printed copy it's a little easier. So here's our nitrate column, and silver's all the way over here. And it says S, and S says soluble. So soluble means that it dissolves in water. Okay, so every time it says S, sorry, I'm trying to get back to the right screen. Every time it says S, that does not mean we write solid here. What we're going to do is write AQ. Soluble means dissolves in water. Okay, so then let's check out silver and sulfide. So here's silver. The sulfide is down on the second to the last row. So this one says I. I means insoluble. Insoluble meaning it does not dissolve in water. So that's a solid. So if we did this reaction, we should have seen a solid precipitate that forms. Okay, and then we already figured out acid means AQ, and I just told you that hydrogen sulfide is a gas. Okay, so now this is our complete answer. This is the total. This is the thing we want graded. Now when you do this on your own, it's going to get messy. Don't be scared of that. I suggest doing it on scrap paper and then copying your answer over. Okay, that's the best approach. When you do your test, you're going to want to take a photograph or a copy of that work and send it to me by email. All right, so for this one, I want you to do this one. I'm going to grade it for you when you turn in your notes next week. All right, so moving into the quantitative part, we're actually going to pause here and I'll upload this video for you to look at, and then we'll pick up from here in the next video. I just want to tell you that I love propane. This is the thing that burns in your grill. I love propane because it looks like a tiny puppy. See, little legs, totally adorable. Okay, so we'll pick up there in the next video.